In this project, we'll measure constant voltages and currents using a digital multimeter, or DMM. Naturally, the demonstrations I do in this video will use a specific DMM. However, most DMMs work about the same way, so these instructions should apply regardless of what kind of DMM you use. DMMs come in a variety of styles. This one is a handheld version. DMMs perform various functions, so one feature is that there's a way to select the desired function. In this case, it's a knob that you turn. The settings that we'll use most in this class are V and MV with a bar over it, the ohm symbol, and A, MA, and MUA. There are also multiple ports or holes where you can plug in leads to connect to your circuit. Typically, the ports are labeled as COM, volt ohm, MUA and MA, and a separate port for A by itself. When using a DMM, you have to make sure that the ports you're using are consistent with the type of measurement you've selected. The type of measurement you're making also dictates how the leads are connected to the circuit itself. This is the circuit that I'll use to demonstrate voltage and current measurement using a DMM. The first thing I'll talk about is measuring constant voltages. Voltage is an energy level difference between two different points in a circuit. As with any other engineering parameter, voltage has to have an assumed sign convention in order to properly interpret the values. The choice of sign convention doesn't depend on the actual voltage. It just affects how we interpret the sign on the value. Changing the sign convention changes the sign on the voltage values. Voltage sign conventions are indicated by a positive and a negative sign on the circuit schematic. The plus sign denotes the assumed higher voltage, and the minus sign indicates the assumed lower voltage. On my diagram, V1 is defined as being assumed to be higher here relative to here, and V2 is assumed to be higher here than here. This doesn't imply anything about the actual relative signs. It just gives us a way to interpret the measured voltage values. To measure a constant voltage, the selected function has a V with a solid and/or broken bar either above it or to the right of it. You connect the COM port to the assumed negative voltage terminal, and the port labeled with a V and usually an ohm sign is connected to the assumed positive voltage terminal. So to measure the voltage V2, connect the COM terminal to the negative terminal and the volt ohm port to the positive terminal. If you swap these leads, the sign on the measured value will change. For example, if we use this voltage sign convention for V2, we would connect the volt ohm terminal here and the COM terminal here. The way we connect the DMM ports to the circuit is dictated by our assumed sign convention. Likewise, to measure the voltage V1 with this assumed polarity, connect the volt ohm terminal here and the COM terminal here. This is the circuit implemented on a breadboard. The resistor connects the positive terminal of the battery to the anode of the diode. The cathode of the diode is connected to the negative terminal of the battery. First, I'll connect the leads to the appropriate ports in the DMM. To measure a voltage, insert one lead into the COM port and the other lead into the port labeled with a V and an ohm sign. There may be other symbols on this port as well, but we won't worry about them yet. In order to measure a constant voltage with your DMM in units of volts, twist the dial until the indicator lines up with the V with a bar over it. To measure in units of millivolts, use the MV position. In our circuit, the voltage V1 is the voltage across the diode with the anode at the assumed positive voltage. To measure this voltage, connect the volt ohm lead to the diode's anode and the COM lead to the diode's cathode. We get a measured voltage of about 2.1 volts. If I switch the leads, the sign on the voltage changes. It's now negative 2.1 volts. Now let's measure the voltage across the resistor. V2. Our assumed voltage polarity from the earlier slide is that the terminal connected to the diode is at the higher voltage. Connecting the volt-ohm lead to that terminal and the COM lead to the positive terminal of the battery results in a measured voltage of about negative 5.7 volts. The minus sign indicates that the actual voltage polarity is opposite to our assumption. That shouldn't bother us since we know how to interpret the negative sign. Next, I'll talk about measuring current. Current is the rate at which charge passes a point. The circuit I'll use is the same one as before. Current also requires a sign convention. Current sign conventions are indicated by an arrow pointing in the assumed direction of positive current. As usual, changing the sign convention changes the sign on the value. The current measurement function is indicated by an A, usually with a bar either above it or next to it. There are also usually settings with an MA or a μA for measuring current in milliamps or microamps. An important point about measuring current is that you have to break into the circuit. If I want to measure the current in this resistor, I have to disconnect this terminal of the resistor from this terminal of the voltage source. The A port on the DMM is then connected at the tail of the current arrow, and the COM port is connected at the head of the current arrow. The circuit with the DMM connected looks like this. The idea is that the current going into the resistor is diverted through the DMM. The current out of the voltage source enters the A port and exits the COM port before going into the resistor. As with the voltage measurements, reversing these connections will change the sign on the measured current. First, we need to connect the leads to the appropriate ports in the DMM. To measure a current in amperes, insert one lead into the COM port and the other lead into the port labeled with an A. To measure in milli or microamperes, connect this lead to this port. In order to measure the current out of the battery and into the resistor, I need to disconnect the resistor from the battery. Then, if my assumed positive current leaves the battery, I connect my amp port to this terminal of the battery and the COM port to this terminal of the resistor. Now, positive current is leaving the battery, going through the DMM into the A port, coming out of the COM port, and going into the resistor via this lead. Notice that the DMM itself is completing the circuit and causing the LED to light up. Now if I move my function to the A setting, the current is displayed. It's about 0.06 amps. If I reverse these leads, the sign on the current should change. Now you should be able to measure constant voltages and currents using a DMM. I'll talk about some other DMM functions in later videos.